Okay, good evening, everybody. Welcome to our open house. Nice night. I think we'll start out by just real quick introductions and talking about a little logistics, and then we'll get going. My name is John Holtzman. I'm a professor in the Department of Astronomy at New Mexico State, and currently the chair of the department. And I've been working to get this observatory up and running for a long time now, and I'm really pleased. This is our second open house. We did one about a month ago, and so I'm real excited to be doing this. Joining us tonight, we have Dr. Maura Prescott. Maura, hi, how are you?
I'm doing all right.
Anything you want to tell us about yourself?
Yeah, I'm a professor in the astronomy department, and I work on galaxies, so I'm excited for tonight.
All right, great. She gave away, I forgot to say what our theme for the night is, which we're going to talk something about galaxies. So that is why we have Maura here. And we're also joined tonight by Zach Edwards. Hi, Zach. How are you?
Hey, John. How you doing tonight?
Good. You got any few words you want to say about yourself?
I'm the lab manager here in the department, and I'm just excited to see everyone coming out on a Friday evening. Thank you for joining us tonight.
So just quick logistics, since we have a number of people. How many people do we have, Zach? Almost 80 people right now. We have it so that the participants are not going to be by you guys talking or by showing your videos. But we would really love to get your input and your questions. And so the best way to do the questions is to use the chat window. And since I will be moving around and slightly nervous, the best place to direct your questions is to Zach. So Zachary Edwards in the chat window. If you chat questions to him, we'll try to break every few minutes and see whether any questions have come up. So with that, I think we're going to start out how we start all these open houses, which is the kind of idea of this open house is to give you guys a little bit of a feeling for what observing is like as an astronomer, and also to show you a few things through the telescope, not a tremendous number, and to talk a little bit about some of the people that do astronomy and just kind of give a little bit more holistic kind of feeling for what it's like to be an astronomer and what people go through. So in that respect, the very first thing I'm going to do, what we always do when we're starting a night of observing, before it gets dark, it's not fully dark out, is I'm going to go up into the dome and open the dome to start getting the air inside the dome cooled off. And I'm going to switch my video, and maybe while I do that more, maybe you could explain real briefly why we do that.
Yeah, sure. Yeah, so when you're going to be using the telescope, you want the air to be nice and stable for you, so you have the clearest image that you can. And if the temperature inside the dome is different from the temperature outside the dome, which it usually is, if the dome's been closed, then that can set up, turbulence in the air, and that degrades the kind of image that you can get and basically blurs it. So we want to kind of equalize the temperature between the outside and the inside to get the best pictures that we can.
So here we go. This is also our quick little tour of the observatory. I was sitting down underneath the telescope in a little room there, and I'm now going to go up the stairs. Hopefully this doesn't make people too dizzy. And up onto the observatory floor. And so I'll stand back for a second, and that's the telescope that we're going to be using. I'll tell you a little bit more about that in a second. We're in a big round dome, and those two big double doors are the doors that the telescope can look out. So I'm going to attempt to walk around here and not crash into the telescope, and climb my little ladder. I can actually do this from the computer, but it's much more fun to actually come up the little ladder and hit the button. And now, hopefully you guys can see the door opening.
Yep, we can see it, John. Looks good.
And you even hear the sound, I think, don't you?
Yep.
That's good. Okay. Great. I'll show you this, our telescope again. A little more light here now. I'll be showing you more on the slides later, but particularly pay attention to this thing up here. That's where our camera is. And I'll be talking about, oh, there goes the dome rotating around. Here you can see the KRWG tower. So it's going to rotate around. So it automatically will go where the telescope is pointed, and they're ready to do stuff. So now I'm going to head back down, turn off the lights. Okay, the second thing is we're going to take a little look outside, check the conditions. And I have to admit, I have checked the conditions pretty recently, and I can tell you it's kind of windy up here. Hopefully not too windy for us to operate. But if you have a hard time hearing me when I go outside because of the wind, we'll know what's going on. So here I'm going out the front door. We are up on the top of Tortugas Mountain. Sunset a few minutes ago, 20 minutes ago or so. There were a bunch of people up here. A lot of people come up here for the sunset, but they seem to have all left by now. You guys hearing me okay, Zach?
Yes, we are, John. Looks pretty out
All
tonight.
right, good. So you're looking out down towards Las Cruces in the Rio Grande Valley. I love coming up this mountain because it just gives a really great perspective on this place that we live. The natural part of it as well as the human development part of it. Tortugas is used by a lot of things. This is used by the KRWG tower, the site of a local Pueblo ceremony. Pilgrimage comes up here every year, looking out towards the east of the development. So, and that's the building looks nice. Building that used to look this nice. Doors that we just opened up, and looking up at the sky.
It is a little windy, John. We are having a tiny bit trouble hearing you, but we hold most of it.
Move inside. Looks clear is what I was saying. I encourage everyone to go outside and look at the sky sometime. Maybe not right this second. I'm going to talk to you a little bit about some stuff you can see in the sky in just a little bit. So you can see from it being light out that we still have a little ways to go before it gets dark, but that's okay because there's a few things we want to talk to you about before we start observing. One thing I did want to do is a little more of a tour of the observatory. So we just came in the front door. This observatory was built back in the 1960s. And at that time, there wasn't computer control. So every time there was doing some observing, people would come up here and spend the night. And this room was the little office and living quarters. So if it wasn't clear out and you were waiting for it to clear up, you might come in here and you might watch some of the black and white TV. And back in this corner, there used to be a bed and you could take a nap, but we took the bed out of there. But one thing that I found in here tonight that was pretty interesting, and I thought was very relevant to our program tonight, was when I first came up here, I found on one of these shelves a guest book. So here's the guest book from the, I guess it doesn't say guest book. And so the first entry, I don't know if you guys can see this, is from 1964, July 6th, so that must have been soon after the observatory was open. And those first two names, they're G. de Vaucouleurs and A. de Vaucouleurs. Well, that turns out that's Gerard de Vaucouleurs and Antoinette de Vaucouleurs from the University of Texas. They weren't originally from Texas. You could probably guess they were originally from France. And there's actually some connection between the de Vaucouleurs, that was a couple, a husband and wife team, and galaxies. Maura, are you familiar with the name de Vaucouleurs?
I sure am. Yeah. So the name de Vaucouleurs for me is connected with a mathematical equation that we use to basically describe the way the light in a galaxy behaves as you go from the center to the outside. For at least some kinds of galaxies, it has the name de Vaucouleurs attached to it because of their work.
All right. Thanks. Yeah, we'll be talking a little bit more about that. So actually, de Vaucouleurs, there's more of a connection, which maybe you don't realize, being a little younger than me, Maura, which is before the epoch of lots of digital images of the sky and big digital catalogs, people just used to actually make book catalogs of galaxies. And so I actually found one in our reading room downstairs in the main department. This was kind of the reference catalog of bright galaxies, Gerard de Vaucouleurs and Antoinette de Vaucouleurs. First edition, 1964. So right around when they came and and visited this observatory. And this was kind of the primary catalog for galaxies. There were 3 editions: the first edition, the second edition, the third edition, which for some reason, well, it was called the RC3, the Reference Catalog Third Edition. RC3 came around the 90s, and it was really the standard reference for galaxies. When you did a survey, when you wanted to go observe a galaxy, you would look through this book of just columns and columns of numbers about galaxies. And we don't do it that way anymore. The other thing de Vaucouleurs was known for, right on the other side of this page, is this diagram of his own kind of classification scheme of different types of galaxies, spiral galaxies and elliptical galaxies. We'll talk about that a little bit. The third thing he was known for was, I have some nice pictures of the planets. That doesn't have to do with galaxies, but they were taken up here back in the 60s. Those are pretty nice. Another thing de Vaucouleurs was known for is there used to be a big debate about the size scale of the universe, and de Vaucouleurs was in one camp and there were some other people in the other camp, and that was a big debate for a long time, but it's been resolved that the right answer is about halfway in between the 2 camps. So that's another story. Anyhow, I guess we'll come back. Maybe I'll show you one more thing while we're waiting. When in the 60s, when this was established, they didn't have digital cameras, so all the images were taken with film. And so I forgot to turn the light on in here, but this is the old darkroom where the film was developed. In astronomy, when you used film, it was usually film emulsion put on a glass plate. And so you would load these glass plates, load them on the telescope, take an exposure, store them in a dark place, and then at the end of the night, you'd bring them down and do some chemical processing. I did just a tiny, tiny little bit of that when I was a wee little baby just starting astronomy. Maura, I guess you probably never did any of that.
No. I remember being at observatories that still had some of the, the equipment, the dark room and so on, but no, I never got to use it.
Okay. All right, I'm gonna temporarily mute and switch back to my other thing. Okay, you guys back to hearing me? All right, great.
Yes,
all right. Everyone with us? Got my screen?
Looks good.
Any exciting questions come in yet, Zach?
The only question we have right now is, how does one go about avoiding light issues? Because when you were out in the mountain, we saw Las Cruces city line and all the lights. So how does an observatory go about avoiding all these light issues?
Well, it's a real issue. And in fact, the lights of nearby city was what we call light pollution. Most certainly does affect the ability to see faint things. And that's why most research observatories are located further away from population centers. And of course, when this observatory was built, it was, Las Cruces was quite a bit smaller. On the flip side, it's nice to be close to a population center for astronomers to be able to go get back and forth easily. But it's true that if someone was building a new big telescope today, they wouldn't build it here, probably because of the light. So in fact, when NMSU got involved in the construction of a new observatory, which was back in the 80s, NMSU collaborated with a number of other universities and did build another observatory up in the Sacramento Mountains, about 2 hours east of here, where it's considerably darker. It's actually one of the darker sites. So in fact, most of the main observatories, and some of the classical famous big observatories I might mention in a little bit. I will mention the observatory at Mount Palomar in California between Los Angeles and San Diego is now severely compromised. You think Las Cruces has got bright lights, Los Angeles and San Diego has got a lot brighter lights. And it is somewhat compromised by that. But, a lot of communities, in Las Cruces does have some light ordinances trying to control the amount of light pollution. And, we encourage everyone to think yourselves when you have lights around your house to keep your lights pointed downwards. And I think we have these ordinances. They're not always enforced or obeyed, and everything we can do to encourage people and tell people why. It's just the night sky is really a fantastic resource. And we should do everything we can to protect it. Okay, that was a great question. Anything else, Zach?
I did get one question about why when we see an observatory, it has that classic dome shape, and what's the purpose of the dome, and why that dome shape?
You know, I'm not sure I have a perfect answer for that. Obviously, you need to have a roof that can go around, in a circle. Um, and so you can look in any given direction. And so a dome is kind of a natural thing. Not all observatories have dome. In fact, at our Apache Point Observatory, the roof they built there, it's a different kind of building, but it's not a half sphere. It's not a hemispherical. It's actually kind of rectangular. And there's some advantage of that, but actually there's a disadvantage of that, which is when it snows up there, the snow just sits on the top and it doesn't fall off so easily. And sometimes I have to go up there and work on getting the snow off. So that's an advantage of the dome, I guess. Other than that, I'm not sure I know. Any thoughts, Maura or Zach?
I was just thinking about, of course, the Sloan Digital Sky Survey telescope doesn't have a dome. It has a shed that just pulls all the way off. So there are different strategies, and there's telescopes that have hexagonal domes where you actually open them up really wide by opening up big garage doors on each of the flat faces. So there's different approaches people have used to basically protect the telescope, but also allow the air to equalize in temperature when you're starting your observing.
Okay, so I thought here I'd do a brief little thing on a little bit of astronomy by eye. You know, again, we're all sitting in the comfort of our houses doing this, and that's kind of nice, but a lot of the romance of it has to do with going outside. And so, as I said before, I encourage people to go outside and look up at the sky. And just a few things, if you were to go out tonight after this program or tomorrow around the same time, that are visible in the sky. Mars is visible kind of nearly overhead in the south part of the sky, just around after it gets dark. It's kind of a red planet. See it? Coming up in the east, Orion, the constellation of Orion is one of the most recognized constellations with these belt of three stars. That's an easy one for people to recognize. And inside Orion, there's a thing called the Orion Nebula, a cloud of gas where stars are being formed. And I think maybe next month we'll do a program on the Orion Nebula. And that can be seen with a pair of binoculars, really nice. A star cluster, we'll do one of these events on star clusters sometime. There's a little tight, small star cluster called the Pleiades, or sometimes called the Seven Sisters. It's got dozens to hundreds of stars, but there's kind of 7 bright ones. If you've got pretty good eyes, you can discern 7 of them in this tiny little patch. My eyes have gotten a little blurry for that. With binoculars, you can see the Milky Way. You can see Milky Way without binoculars, and along the Milky Way, if you just scan the Milky Way with binoculars, that's a really fun thing to do. And in particular, there's a set of open clusters called H and Chi Persei, sometimes called the double cluster, 2 clusters right next to one another. And another thing that you could see early in the evening, it's going away now, is the thing that we're kind of highlighting tonight, the Andromeda Galaxy, which is, I would say, the very farthest thing that humans can see with their naked eyes. It's a little hard to see with your naked eyes. If you go to a dark place, I'm going to show you a little map about how to find it. But it's not hard to find. It's not hard to see with binoculars if you know where to point your binoculars. So that'll be a challenge for people to go try to do that. And I'll give you a couple little hints for how to do it. So here's some little star charts of finding Andromeda. And let's start with this one here on the right. Some people, if you're completely unfamiliar with the sky, then this will probably be hard to follow, but maybe you'll get familiar. A kind of prominent constellation or that we can see from the northern hemisphere is a constellation called Cassiopeia. It's kind of a W in the sky. Here it looks sort of like a W. Here it is as a W turned over on its side. And this is kind of what it would look like if you went out now looking in the west to northwest direction. And that W of Cassiopeia, if you kind of come to this last part of the W and you kind of draw a perpendicular line through the W to this star, that points over here to the Andromeda Galaxy. So that's one way to find the Andromeda Galaxy. The way I usually find it is through another constellation, the constellation of Pegasus. And Pegasus makes this big square. These are the 4 stars of the square, which right now are just kind of down on the sort of towards the western horizon. So you'd see it. That's why I turned this picture on the side, because that's kind of what it looked like now. And if you kind of go through the diagonal of the square and you come right through, there are these 2 stars and they have these green arrows. I see there's 2 stars, which I go in between to hit this star. And then I make a 90-degree right turn past one little star. And that's where you can find Andromeda. So that'll be a challenge for people. And if you look at that, with your naked eye, you can see a fuzz. And with binoculars, you can see a little more of a fuzz. And who is Andromeda? A lot of the constellations are named after from Greek heritage. I think a lot of cultures probably name stuff in the sky. I'm not quite sure why the Greek heritage is the one that stuck with us, but in the Greek mythology, Andromeda was the daughter of Cassiopeia, this constellation, and Cepheus, this constellation. Andromeda was the daughter. The mom said something bad, someone got offended. She ended up being chained to a rock, got rescued by Perseus, who's right over here next to him. Perseus came by. Perseus, I think, had just killed the Medusa, the multi-snake one. And when they chopped off the head, I think a winged horse came out, and that was Pegasus. That's the square of Pegasus. So that's sort of the quick little mythology behind all these constellations. So it's fun to try to find it this way. Of course, these days, we have easier ways of finding things. And so I recommend these. If it doesn't work, you can get a bunch of apps for your phone that basically you take your phone, I don't know if you can see me, you point it up, there it is, you point it up at the sky and it shows you some stuff. And so anyhow, so this is a picture I took with my phone just this morning when I kind of knew where Andromeda was. It was actually over in the east this morning. Now the Earth is rotating, it's over in the west. And here's what my phone showed me about the Andromeda. And here the great square of Pegasus is up in the other direction, but it was across the diagonal, through the two, hit the one, turn right, there it is. And there's the last part of the W of Cassiopeia pointing towards Andromeda. So anyhow, if you get a phone app, like these are just three, I think there's several other ones. You can point it, get a rough idea of where it is, and then try to see it with your naked eye, or a pair of binoculars is recommended. Another resource you can have, I hear these sky maps. A lot of different websites provide them. I happen to like this one. I think it's www.skymaps.com, which every month they come out with a little map of the sky. And here we are in February. And there's that, once again, the great square of Pegasus, and going out and turning right. And there it all is there. And gives you some list of fun things to see in the sky. So a lot of resources. I encourage people to get out and take a look at the sky and enjoy our relatively dark skies here in Las Cruces. New Mexico is one of the darkest places in the continental US. So if you get out, outside of Las Cruces, pretty spectacular. All right.
John, if I could just add one thing to, seeing Andromeda with the naked eye. I just learned a couple of years ago that a great place for that is the Aguirre Springs campground on the other side of the Oregon Mountains. I was camping there and happened to wake up in the middle of the night, looked up and saw a little smudge. It was very, very noticeable. So I recommend that.
Yeah, that's great. Yeah, I mean, anything to block out Las Cruces. So a quicker thing is just come behind the backside of Tortugas Mountain. There's a parking area on the backside of Tortugas Mountain. I think that'd be a good place. So although it's great to look up at the sky with your eye, there's only so much you can see with your eye, and there's kind of two reasons. One, our eyes are not that big, and so they can't collect that much light. And another thing that our eyes can't quite do is they can't sort of collect light over a long period of time and then say, show me the image after you've collected the light. Our eye is kind of constantly taking snapshots all over the place. And so observatories are built to kind of, get around these limitations of our eye. So how does it work? There's basically two main components: telescopes. And basically you can think of a telescope as a big eye, right? As a matter of fact, the Palomar 5-meter telescope, its nickname was the Big Eye. The Big Eye. Then they had a smaller one there that for some reason was called the Pig Eye. I'm not quite sure, for Palomar, I guess. Anyhow, the Big Eye telescope is a big eye, just collects light over a much larger area and focuses it all in one place, so you could see fainter things. And then two, these days we don't look with our eyes through telescopes, we have cameras with the back of telescopes. And what cameras have the ability to do is they have the ability to collect light over a period of time, and then showing you the picture after it's accumulated the light over a longer period of time. You'll see if we're looking at faint things like galaxies, like we're going to do tonight, they're faint, and we're going to have to take exposures that take a little bit of time, a couple minutes. When we looked at planets last month, planets are bright, and we could take an exposure in half a second and see things. They were almost too bright, and it's kind of the opposite problem. But tonight we're going to actually have to expose for a little bit of time to see the faint things. All right, here's our telescope that we're going to be using tonight, a 24-inch telescope. When people talk about the size of a telescope, they're talking about the diameter of the primary mirror, because it's really the area of the mirror that determines how much light you can collect. So it's not how how long it is, it's how big it is across, because that's the collecting area. The light comes down and is collected by a mirror down at the bottom end of the telescope. This telescope was built originally mostly to look at planets in support of NASA planetary missions, and it was used kind of into sort of the first really strong epic of sending space probes to some of the nearby planets. NASA wanted a good record of the time variability of what planets looked like before the Voyager Pioneer missions went out there. And this telescope was kind of fundamental in providing sort of a long-term archive of planets and changes in the planets. And it was run up through the mid-90s, which is right around the time when our Apache Point Observatory got built. And so when that happened, this telescope pretty much stopped being used. It sat for a while, and I used to come up here with my kids and think, gosh, we should do something with this telescope. Anyhow, it took a little while, but about 10 years ago, we partnered with a professional amateur association called the American Association of Variable Star Observers. And they had some people that wanted to build an observatory in the Southwest. But instead of building it, we said, well, let's refurbish this one. It's kind of a mutually beneficial thing. They contributed a little bit of funds. We did some work with some NMSU engineering students to kind of modernize it, computer control it, replace some of the motors. And we've been using it on and off ever since then. And then just last year, we did a renovation of the outside part of the building, and we're starting to do these public houses, these public open houses. So I think it's great. What else? So where does this telescope fit in the context of other telescopes? So this is just quickly how our telescope works. It's almost a perfect model of it. The light comes in from the sky, comes down through the tube of the telescope, and the main mirror of the telescope is down at the bottom. And it's a curved mirror, so it takes that light and then focuses it up towards the top. And there's a little mirror at the top that's a flat diagonal mirror, and it takes that light and turns it out to the side, where the light coming from all across the house, 24 inches of aperture, all gets focused to one point right there. And that's the point where we put our camera. And so that's using the telescope as a light bucket. As light buckets go, this telescope is a little one. This is kind of a diagram of some of the big telescopes of the world today. And the smallest one on this thing is maybe this Yerkes Observatory 40-inch refractor. And so ours is a 24-inch, so it's smaller even than that little blue circle. So we're a little baby on this one. The Apache Point Observatory, 3.5 meters, about this big on that one. And so that was pretty big when it was built back in the early 90s, but not so big anymore. Now we're building bigger and bigger telescopes. The biggest single mirror telescopes are telescopes that are like 8 meters in diameter. A telescope called Gemini North, Subaru North on Hawaii. There's a Gemini in Chile. Oh, there it is, in Chile. And then to get even bigger telescopes, people are starting to put lots of mirrors together. So there was a pioneering kind of telescope called the Keck telescopes in Hawaii. I don't know why they don't have the diagram here, but they look kind of like this one. It's lots of little mirrors put together to make one bigger mirror. And now people are starting to take telescopes with lots of big mirrors and putting them together. So this telescope is under construction in Chile right now. And then an even slightly bigger one is maybe under construction. And that's lots and lots and lots of little mirrors to make a telescope that's 30 meters across compared to our little 0.6 meter across telescope down here. So what's the biggest telescope you ever observed with, Maura?
The biggest one, I guess it would probably be the Keck telescope. The 2 telescopes, each 10 meters across. So I've used one of them. That would be the biggest one.
I think I used this multiple mirror telescope when it was a multiple mirror telescope.
That's one of my favorites, actually, the MMT.
Right, that's near Tucson, which is where Maura went to graduate school. And just for a scale of these things, here's a tennis court and a basketball court on the same scale. So some of these things are really, really pretty tremendous. So anyhow, we're going to use our little one tonight, because the big ones are being used. Here's the camera we have up at the top end of the telescope. And so basically the idea of a camera, since we're going to be taking some pictures with this camera, the basic idea of how these digital cameras work is they have a little sensor inside of them that basically counts up every time a little packet of light, something we call a photon, hits it. And so basically a digital image is just recording how many photons hit at each different location. That array of numbers is then converted into an image on our computer screen. And we'll be looking at some of those images, and we'll be looking at some of the numbers. And so I used some pictures we took from last month to try to demonstrate. So here is just a picture of some stars. And if you just zoom in a little on this region, you can see there's a couple stars. I'm not sure what those fuzzy things are. We zoom in a little bit on this one star. We zoom in even further on this one star. And now I've actually just stuck on top of the image what the numbers of proportional to the number of photons counted in each one of these locations. And so the highest number looks brightest, and the lowest number is the part that looks fainter. And so that's how we make our pictures. That's what a digital image is. And there's two main things that we can kind of measure from these digital images, something called brightness and something called surface brightness. And brightness refers to, the total amount of light from an object. So if I were to go back to this star, and I would just take all these numbers and add them all up, I'd say, oh, that's how bright the star is. I could just total them all up and I get the brightness of the star. And that's what's relevant when you look at an object that just looks like a tiny little point. And stars, even though stars are big, they're so far away that they're essentially tiny little points from the vantage point of Earth. They look a little bit blurred out here, and you say, well, it's not a tiny point, it's spread out. But the spreading out of starlight comes from blurring in the Earth's atmosphere and a tiny little bit from blurring from the telescope, but mostly blurring from the Earth's atmosphere. So the distribution of these numbers would change whether it's a good night or a bad night, but the total number wouldn't change from night to night. And that's different from a galaxy or a planet, where a galaxy is actually big across the sky. So you can measure the brightness per area in the sky. And that's what surface brightness is. And so we're going to see that there are some galaxies that have high surface brightness, which is lots of stars packed into one area in the sky, and some galaxies that have lower surface brightness, more diffuse starlight. And so this actually schematically sort of shows a graph of surface brightnesses of galaxies. And there are some galaxies like this red line that are very bright in the centers, and there are some that are less bright in the centers. And this is how they change. They get fainter as you go out, and some get fainter gradually, and some get fainter very quickly. And this red line is the line that Maura was talking about earlier, called the de Vaucouleurs profile. And there they are, Gerard and Antoinette de Vaucouleurs, who signed the register over in the other room. So all pretty cool. All right. What else do we got? We're getting there. Getting dark enough outside, I think, almost. Quick little thing, the pictures we're going to take tonight are going to be black and white pictures. Most detectors now can't sense what kind of photon they're taking. So light of different colors has different character photons, but they're all photons of light. And the way we get color information in astronomy is we put a piece of colored glass in front of the detector. So you might take a piece of red glass and take a picture, and then you get the brightness of an object in red light. Then you might put a piece of blue glass in front and see what the object looks like in blue light, maybe a third picture of what it looks like in green light. And then you can use computers to put those all together into a color picture. But we're not going to do that tonight. Maybe that'll be some other open house. We'll figure out how to do that. I think most of the pictures we're going to take tonight are going to be with the red filter, and we'll see what things are looking like in red light. Okay, so I think with that, hopefully, what time is it? 6:35, just exactly what's called nautical twilight. The sun is now 12 degrees below the horizon. It's not fully dark out, but hopefully it's dark enough for us to see something. So I'm going to switch over now. Let's see, you got any questions coming in, Zach, or any comments from either you or Maura?
I do have a question that just popped up, and it actually might be a good question to ask now. So when using a telescope, is there any calibrations that need to occur before each use, after each use, and what does the telescope need to do to be calibrated or focused?
Well, that's a good, both. So there are a couple of things. Focusing is an important thing. Maybe we'll focus. Maybe we'll take a picture and see whether we're out of focus, so we don't spend too much time. But it's actually, the temperature's gotten a little colder, so we might be a little bit out of focus. So typically what people do to focus, maybe we'll do it, is you just look at a star and you move that camera back and forth ever so little, and you take a series of pictures and see which one is the sharpest. And that's basically the idea of focus. As far as calibration is concerned, if you're trying to make very accurate measurements of brightnesses, you do have to pay attention to things like whether the detector is equally sensitive in all regions. And there's a series of calibrations that you do to do quantitative stuff, but I think we're not gonna go into that tonight. Maybe it'll be another subject some other time. Okay, so let's see. So I bring up here, this is now our little desktop for the telescope control. And one thing that we have up there that's kind of fun, I gotta find my mouse. There it is. One thing we have upstairs is we have a webcam, so you can actually see. We have two webcams. We have that one, and we have another one that's looking at the dials. I'm going to turn the little lights off. These webcams are kind of cool. They have little built-in lights in them, but the lights that the webcams have them are kind of in the kind of light that our eyes can't see. It's a near infrared light, and so we can actually leave these camera lights on and still take pictures in red light, and this near infrared light won't interfere with our pictures. We can actually watch the telescope moving around and doing some stuff. So there it is over where we saw it before. And so I think the first thing we're going to do is we're going to what's called slew, move the telescope as fast as it can, which isn't that fast, over to the Andromeda galaxy. And these days it's pretty easy. All I have to do is click a little window that says slew and type in the magic code number. M31 is the astronomer's name for the Andromeda galaxy. It's from the catalog made by a guy named Messier. That's the M part. And now we can watch the telescope moving over. Andromeda's over in the west part of the sky. We were pointed down in the southeast. So we're moving over there. The dome's moving around. It knows where it's got to go. Maybe I can steer this webcam up a little bit. You can see a little bit. It's probably going to end up kind of pointing sort of near us. So we won't be able to see the top of the telescope. That big white thing over there, that's actually is used for calibration of sensitivities. When you do those calibration things, you might point the telescope at that white thing and then see whether you get a uniform brightness image. And if you don't, that's how you calibrate the sensitivity of the detector. So just relevant to the question we just had. So let's see, maybe we're pointed over. It's kind of, and it says, and it still says slewing there, it means it's still kind of honing in on the right area. At least that's what we hope it's doing.
Looks like we've got some wind up in the dome. Things are, little bits of dust are flying by the camera, it looks like.
Okay. That was a little windy out. All right, so now that maybe we're pointed at Andromeda, there's the dome adjusting itself a little bit. I think we'll shoot to take our first picture. So this window here is where we have our images coming up, and this window here is where we control our camera. So I think our first image we're going to take, change a few things. One thing I meant to do, I'm going to do it now. There is another setup thing that I forgot to do before, which is our detectors, since we expose for a long period of time, our detectors are generally cooled down because otherwise they have a kind of electronic signal. And so right now our detector is being cooled to minus 12 degrees. But I'm going to see whether maybe I can, well, maybe I won't worry about that right now. All right, so let's take our first picture. Let's just start out by taking, what do you think, Maura, 1 minute? Or should we
Sounds good.
All right, let's try a 1 minute exposure. So this is the part where you're looking at something that's a little bit faint, and we have to wait a little while. So 60 seconds, that's not too long. Any questions in our 60 seconds?
This might take longer than a minute, but what's the best way to become an astronomer? What would one have to study in school?
It's kind of interesting. We have a graduate program in astronomy at New Mexico State, and we have people who in their undergraduate, a lot of them majored in astronomy. A lot of undergraduate schools don't have astronomy majors. Probably the next most common one is physics major. But really, could be any natural science. If you do reading and have curiosity, that's kind of mostly what it takes. But usually the educational background is either in the astronomy program or in physics. Physics is kind of the heart. I mean, astronomy is a great science, depending on what you study. If you study planets, then geology is relevant to stuff. And sometimes there's a new field of astronomy called astrobiology, so even biology can be part of stuff, or chemistry can be part of stuff. Astronomy is kind of a great crossroads kind of science. Okay, so let's see. So I see a picture over here. So there are a couple things. I don't see a galaxy in that one, but that's okay because we're not seeing the whole picture. And lo and behold, they're right in the middle of the picture. There is the Andromeda Galaxy. And in fact, it's pretty nice. So a couple things. Let's see, maybe I can make this bigger for one thing. That'll probably help. I can make this one bigger. So there we can see that's actually just the very central part of the Andromeda Galaxy. The Andromeda Galaxy is the nearest big galaxy to us. So all these other things here, these are stars. And those are stars in our Milky Way galaxy, just happen to be in the direction. I'll show you that the Andromeda Galaxy is actually not located that far from the plane of our own Milky Way galaxy that we live in. So when we look at the Andromeda Galaxy, we're looking through a fair chunk of our galaxy. And so those are the stars we see. These stars actually look pretty blurry because I think it's gotten colder out, and I think we probably could focus the telescope. But for galaxies are kind of big blurry things, and so having a sharp focus not going to really change the look of the galaxy that much. So, I was talking about digital imaging, and so what is this picture? If I move my mouse around here, you can see down here in the lower right, well, sometimes there's some numbers, right? And those are the numbers that are under each one of the pixels, right? And so that's basically given the number of photons that hit in each area of the galaxy. And you can see here, the center part of the galaxy is all whited out, and there's a translation between the number that's recorded by the detector and how bright we make it appear on the screen. And we can actually control that, and that's what this window shows over here. There's a little red arrow and a little green arrow, and basically that's saying is things at the level, imagine this is a graph, the lowest numbers on the left and the highest numbers on the right. And so this says anything lower than the red is going to be black, and anything higher than the green is going to be white. And so we can actually change what the image looks like by changing, that's called changing the contrast. And so if any of you ever used to have old TV sets where there were two buttons, brightness and contrast, well, that's like separating, contrast is separating the green from the red, brightness is sliding green and red together. So we can make the digital image look different, even though it's the same picture. So now we're kind of seeing the full range, from the darkest areas to the brightest areas. You can see that Andromeda's got a really bright, condensed central part, a bright nucleus of the galaxy. Actually, the center of the Andromeda Galaxy, as the center of many other galaxies, actually harbors a black hole in the middle of it. But maybe that's a subject for another time. But one thing I thought we might talk a little bit about is surface brightnesses of galaxies, and recognizing that galaxies, there are some that are real dense and concentrated, and there are some that are more diffuse. So we can actually measure that here. So let's see if we can do that. If we go march around to the center, what are the biggest numbers that we're seeing around the center, Maura?
I'm seeing about 13,000.
About 13,000 or 14,000. And so let's keep that in mind. That's 13,000 in 60 seconds, right?
In 60 seconds.
You can make a little note of that.
Sure.
All right. And let's see. Let's go look at one other galaxy, and then I want to segue to talking a little bit. Let's go look. There's a very nearby galaxy. It turns out the Andromeda Galaxy is nearby to us, and it's a big galaxy. And actually what we're seeing, and I'll show you this on a slide in a little bit, is actually, even when we crank up the contrast and see that it's almost filling this picture, right? We're actually still only seeing the very center part of the Andromeda Galaxy. It extends way off the big size of this computer screen, as we'll see in a little bit. And it's got a couple little smaller companion galaxies, and one of them is called M32. So that's pretty close here, so it should be pretty quick to get to. So Andromeda Galaxy is a galaxy called the spiral galaxy. It's kind of got a roundish region in the center called the bulge, and then a big kind of flattened disk of stars, kind of like our own Milky Way galaxy. This galaxy that we're slewing to now, did we really get there already? Maybe. M32 is a compact elliptical galaxy, and they're much more concentrated, so they have a higher surface brightness. So let's see if we can take a 60-second exposure a bit. Any questions come in during our 60 seconds, Zach?
I know when we were talking about the sizes of telescopes, you mentioned several were in Chile, and we mentioned that light pollution is a thing. But why is Chile prime real estate for some observatories or a lot of observatories?
I think it's a good question. So Chile has a big mountain ridge along the western edge. Chile is all along the western edge of South America, and so they're tall mountains. So that's good. If people like to build observatories up high because there's less atmosphere to look through, so a little less blurring, a little less absorption of light if you go high. And it's also relatively dark there. The observatories there are mostly away from major urban centers. Also, I think the prevailing winds there tend to be like they are from here from the west, and so that tends, when you have a jagged set of mountains kind of on the west edge of a continent, that tends to make for good seeing conditions. And a very important reason, it's clear a lot of the time. It's not cloudy, right? That's kind of an important consideration. I'm doing a project that's partly working at an observatory in Chile, and we were shut down for a long time last year because of COVID. And that observatory opened up in October, and we were just finishing up a survey, and we extended the survey a little bit, and the survey actually just finished 2 weeks ago. And in that time, from the end of October to the middle of January, we observed every single night. There was not one cloudy night. That's unusual even for Chile. It's a little scary in terms of global climate, I think, but it was pretty extraordinary. Okay, we got our picture of M32. M32 is not super big. It's really small. We're just seeing the compact central part of it, and that's almost all of it. It's possible that M32 and M31 had some interactions, and that the outer parts of the stars of M32 might have been stripped off by the gravity of Andromeda galaxy. That's something that people have talked about. But let's go do our quantitative thing again, Nora, and let me adjust the contrast a little bit here. And now I get to adjust the contrast way up to see this thing. And so let's go see what we see in there. So what are we seeing? I might need to zoom in a little bit. How about that? All right. What are we getting?
I'm seeing like 21,000.
So clearly brighter than Andromeda. Actually, not as much brighter as I thought it was going to be, and I think I know why that is. And that's, I could tell from looking at this star. That star is just blurred out, but our center of Andromeda is pretty blurred out by the fact that we're a little bit out of focus because we haven't spent the time to focus. So, all right, so that's interesting. Okay, so let's see. I'm going to break away from this. We're going to come back and observe maybe one other galaxy in a little bit, but let me just break away for a minute or a couple minutes and talk about a few other things. Let's see. You guys are still seeing that screen, right? What do we want to talk about? So the Andromeda galaxy. So one thing, just to sort of emphasize more, I found this cool little picture, which, Andromeda, it's relatively low surface brightness. So, to our eyes, it looks like a faint little fuzzy patch. We need to use a telescope to see it. But it's actually a pretty big galaxy. And it actually, if it had a higher surface brightness, it would take up a big area in the sky. And so that's kind of demonstrated by this little graphic. So here someone went into this photo and put an image of Andromeda. If it was quite a bit brighter, it would look something like that in the sky. So the Andromeda galaxy itself is bigger than the full moon across. In binoculars, you won't see that. But anyhow, we were just looking at this very central part of Andromeda there. So that's kind of an interesting thing. Second thing I wanted to talk about is what we're trying to do in these open houses is talk a little bit about people. And I don't know, Maura, do you want to introduce the idea you had about story packages and what that's all about?
Sure, yeah. So this is something that we've been working on in the department in our, we call our inclusive astronomy group. The idea was to basically collect some, information, stories about different astronomers who've made contributions, and to really, not just talk about the science that they've done, but also talk a little bit more about their life and the challenges that they overcame. So we've been working on that for about the last last year or so, collecting information on a number of different people. And Vera Rubin is one of the people that that we've been looking at, that John has here on the slide.
Yeah. So do you know anything about Vera Rubin, Maura?
Well, yes, it's a famous name in terms of galaxy work. I met her one time. I was at a conference, a women in astronomy conference, and I was far too timid to say anything. But I remember standing in a big group of impressionable young astronomers, listening to every word she had to say. That was my one time brushing by Vera Rubin.
That's cool. Yeah, she was a pretty influential person. So here, she was born in 1928. She died a few years ago. And really kind of what a pioneering thing she was is she was a extremely successful woman in astronomy in an era when there weren't that many women in astronomy. And she felt very passionately about that, and was a big advocate for women in astronomy. And she had to, overcome some hurdles doing astronomy in a time when it was largely male dominated. She was the daughter of an immigrant, and she knew from an early age. She wrote a nice little autobiography about 10 years ago, so that's where I'm getting some of this stuff. She knew from an early age. She said, "I can't imagine living without trying to figure out something about the universe that we live in." It was just a passion of hers ever since she was a kid. She built a little telescope when she was a kid. Wanted to go to school. She ended up going to undergraduate school at Vassar, where there was a famous woman, Mariah Mitchell, astronomer there, and I think she was inspired by that. She was keen to go to graduate school, and she was particularly interested in going to Princeton, but Princeton did not accept women at that time, so she didn't go to Princeton. She ended up going to Cornell University for a master's degree, worked with some physicists there, including the famous Richard Feynman, and then ended up getting a PhD at Georgetown University in Washington, D.C. And kind of amazing things, she kind of, did it all. She had 4 kids, had kids while she was doing her graduate degree, and somehow managed to do that. And she said she was fortunate that she had a supportive family. I think the grandparents looked after the kids some, and she had a supportive husband. But it was a challenge, and at a time when people did not readily accept that. So here's a few pictures for doing a variety of different things. So a few things that Vera Rubin contributed related to galaxies. One thing she recognized is, it was recognized much longer before, that we live in what we call an expanding universe, all the galaxies flying apart from each other, the whole universe is expanding. But there was some question about whether all the galaxies were expanding uniformly, and Vera made some measurements that suggested that galaxies were not all moving apart from each other uniformly, that galaxies move in space relative to that uniform expansion. And in fact, she measured that our little group of galaxies, the Milky Way and Andromeda, seem to be moving relative to this general expansion. This is an area it was an effect that was called a long time ago the Rubin-Ford effect, and it was not well accepted for a long time, but now it's super well accepted. It's like totally standard. And in fact, Andromeda and Milky Way galaxy are actually moving towards each other, and we're actually going to collide with the Andromeda galaxy. But not to worry, it's going to be in a few billion years. I have a little simulated video, but maybe I'm not going to go to it now. We're going to talk about a few more things, and we'll talk about it later if we have any time. The most famous thing that Vera Rubin was known for was studying rotation of galaxies. In these spiral galaxies, the stars go in orbits around the center of the galaxy in a similar way to the way that planets go in orbit around our sun, and they go around for a reason. It's called gravity. Gravity pulls objects in orbit around a more massive object, and so just as planets in the solar system orbit around the sun, stars and galaxies orbit around the center of the galaxy. And so what Vera Rubin's contribution was, she studied the speed at which the stars rotated around the center of the galaxy as a function of how far away they were from the center of the galaxy. In our solar system, if you study this, you find out that the inner planets move fast. Mercury moves the fastest, Venus moves a little slower, Earth moves a little slower, Mars slower, Jupiter slower, Saturn slower, Uranus slower, Neptune the slowest, right? And we understand very well why that is. It's because when you get further away from the sun, which is the source of the force of gravity is weaker, and so And so when people looked at galaxies, they said, well, a galaxy doesn't look quite like the solar system. It's not like there's one bright thing at the center, but it's clear that most of the stars are at the center, and it's kind of dwindling out as you go further out. So people said, well, it's got to be the same. We understand gravity. When you go far away from the center of the galaxy, the speeds are going to start going down. And so Vera looked at some galaxies to see if this was the case and found out that it was not the case, right? That in fact, stars were moving just as fast in the outer part of the galaxy as in the other. And so just here it is, there's a paper on the M31 galaxy, rotation of the Andromeda Nebula. Vera Rubin and Kent Ford was a longtime collaborator of Vera's who did instrumentation work in 1970s, measuring really for the first time that the outer regions of the Andromeda galaxy were moving as fast as the inner regions. And so maybe I think I do this as a picture. Yeah, so here's the little picture from Vera Rubin, actually, not from that paper, but from Vera Rubin of the Andromeda galaxy. And this little graph kind of shows the speed of stars. They're not stars here. As you go out along this line, it's measuring vertically how fast the stars are moving. And in the center, they're moving slower and they get faster. I don't know what this strange gap is. And then as you keep going out, these stars are all moving at about the same speed. Even when you get out, these points are actually not measured from stars. They're measured from gas. There was another guy, Morton Roberts, who was studying this in hydrogen gas. And way past where you saw stars, the speed of the stars, the speeds of the stuff, the stars and the gas were not slowing down. And people said, that's very strange. If most of the mass is where most of the light is, then these things should be going slower than these things, and they were going the same speed. And so that's been a great mystery. It continues to be a great mystery. There's now a commonly accepted explanation for it, and that's that there's actually a lot of mass in galaxies that we can't see. So although it looks like galaxies are concentrated toward the center in light, we think in mass, there's actually a lot of mass all the way out here where we can't see it. And we don't exactly know what that mass is made up of. And so astronomers call it dark matter that we can't see. And it's still not known what that dark matter is. And not everyone believes that it exists. Other people say, maybe we don't understand gravity that well, but there's a lot of experiments that suggest that we understand gravity pretty well. And so the most commonly accepted explanation is that the universe is filled, galaxies are filled with this dark matter. And there might be as much as 10 times as much dark matter in a galaxy as there is luminous matter we can see. And there's an intersection. We were talking about intersections between different fields. Physicists study, some physicists study what's called particle physics, very small things. And one leading idea for what dark matter is it's some new kind of subatomic particle that maybe is very common in the universe. And so physicists are actually devising experiments to try to search and detect for a particle that might be a dark matter particle candidate. And I'm somewhat optimistic that in our lifetime, even in my limited remainder of my lifetime, may have yet to see, the identification of what dark matter actually is. So that's kind of the contribution that Vera Rubin is most known for. But there's really a third thing that I think is really important, and that we already mentioned, that she was really a champion for women in astronomy. She mentored a lot of female astronomers. She advocated for hiring women in faculty positions, having them give talks, getting awards given to them. She even advised the Pope on it. And as a mentoring story, I will say that Vera Rubin is my grandmother. Not really, but she's my academic grandmother, sort of. So my advisor, my PhD advisor, was a woman named Sandy Faber. I did my graduate work at University of California in Santa Cruz. Sandy was a graduate student herself at Harvard, but Sandy also was married and had kids. And she ended up relocating with her husband while she was doing her graduate degree at Harvard to Washington, D.C., which, remember, Vera Rubin graduated from Georgetown, and she got a position at the Department of Terrestrial Magnetism in Washington, D.C. And after, I think Sandy originally didn't have a good place to work, but she eventually got an office in DTM, the Department of Terrestrial Magnetism, where Vera Rubin was. And she basically said Vera Rubin was not her official advisor, but she was her de facto advisor. So Vera was Sandy's advisor, Sandy was my advisor, so Vera is my academic grandmother. So you had any important mentors in astronomy, women or otherwise, Maura?
I'm sorry, what was that?
You had any important mentors in astronomy, women or otherwise?
Well, certainly, yeah. I mean, I would say my undergraduate advisor was definitely a big role model for me. He's just this infectious enthusiasm, and he got me to the telescope very early on, so I got hands-on experience. And while we were there, one of my memories of being at the telescope with him was he had 2 small kids at the time, and he would get everything started for the night. We'd start working, and then he'd duck away and go call his kids and check in on how they were. So he was being a good dad even while I was being an astronomer.
And who was that? What was his name?
Bill Cutts at the University of Wisconsin-Madison.
Cool. How about you, Zach? Do you have any inspirational astronomy stories?
My undergraduate advisor, Dr. Rosa Williams, was a huge influence of getting me into astronomy and getting me started down astronomy and the education side of astronomy. So I think a few people from my undergrad are watching, so shout out to Dr. Williams.
All right, cool. I guess, oh yeah, so that's a few things. Vera Rubin, it was in the news recently. Anyhow, she won some awards, but what she was in the news just a year or so ago is there's a big telescope being constructed. Whoops, I'll say this first. I just got this today. I got an email from a friend of mine who actually organized a conference in honor of Vera Rubin about 10 years ago. I tried to get him to join in on this, to tell us some stories, but he wasn't able to. But he just clued me in today that there's just a book that's just about to come out on Vera Rubin. These are not my friends, but they've written a lot about astronomy. And so if you're interested in Vera Rubin, there's a book that's about to come out. Pioneering scientist who made significant contributions to our understanding of dark matter and championed the advancement of women in science. So that's fun. Yeah, this is what I was going to say. The Vera Rubin Observatory, an observatory being built in Chile. We were just talking about it on a mountain called Cerro Pachón. This is a pretty exciting observatory. It's under construction right now. It was slated to start operating maybe later this year, but I think with COVID, it's delayed probably a couple years. This is an 8-meter diameter mirror, but it's an 8-meter telescope with an extremely huge camera on it. And the idea of this telescope, and you can see here's like a different kind of dome. Maura was talking about different kinds of domes. There's a different kind of dome. The idea of this telescope is it's going to be used to do a big survey of the whole sky. It's going to take pictures of the entire sky with an 8-meter telescope. But it has such a big camera inside of it that it can step around and take pictures of the whole sky like once every week or two. And then it's going to do it again and again and again and again and again. And so that's going to do 2 things. One, over time, in any given region of the sky, it's going to build up more and more signals. So we'll see fainter and fainter and fainter and fainter things. But by splitting those exposures to every couple of weeks, it's also going to let people study things that change in time. Astronomy is not all static. There are things that change in time, things like supernovae explosions that go off, and it's going to detect those. And there's a lot of science goals of the Vera Rubin Observatory. One is kind of studying the largest scale things, cosmology and the expansion of the universe. And then there's a component in studying solar system things and planets around nearby stars. So it's going to be kind of a kind of treasure trove of imaging survey science over the next 10 or 15 years, I think. So you can look out in the news for that. So that's our little digression. So let's go back to the telescope and maybe observe another galaxy, and then maybe Maura is going to tell us a little bit about galaxies, and we'll wrap this up. We already looked at M32. Here's what Maura will tell us about galaxies. I think we're just going to look at one more galaxy, a galaxy called NGC 891, which is thought to be a galaxy similar to our own Milky Way galaxy. So let's see if I can go back and get our telescope back, and let's see if we can slew over to NGC 891, and we'll do that. And let's see if we can watch ourselves go in there. This one's a spiral galaxy, a little lower surface brightness. I think we decided that maybe 2 minutes would be okay. Is that right, Maura?
That sounds about right.
100. 120 seconds. Okay. Anything you're going to want to contribute in these 120 seconds, either questions from the audience or comments from Zach or Maura? What do you find inspiring about galaxies, Maura?
About galaxies? I don't know. I mean, I guess I like all areas in astronomy, but I just got captivated by the complexity of them. And I'll talk about some of that in a few minutes. I guess if you were talking about astronomy as a field being kind of a crossroads of lots of different scientific fields, galaxies in a way are kind of a crossroads of different things within the field of astronomy. You can talk about the stars and then the gas and then the dark matter, the dynamics. There's just a lot going on. So I think I like that complexity.
Right, that's exactly what I was going to say. Galaxies, I used to teach the graduate class in galaxies, which now Maura has taken over and does a much better job with. But I used to introduce it as galaxies as the crossroad of astronomy. Galaxies are collections of stars and gas and dust. And so kind of on the small scale, that's what builds up a galaxy and dark matter. But then galaxies themselves trace out the large scale structure of the whole universe. So galaxies are on the small side of cosmology, the study of the whole universe. So it's really this intersection of the smaller scale. In astronomy, smaller scale is stars, which is still a pretty big scale, up to this intermediate thing, up to the biggest scales of cosmology. And then it actually kind of wraps around, because it turns out that cosmology, the contents of the universe matters, and dark matter, and maybe this other thing called dark energy might be an important component of the universe. And that may actually be microphysics, wrapping right around back to the smallest scale again. So astronomy's kind of got this, it's often represented by this snake eating its tail, going from small scales to big scales and then back into small scales again. And look, we can wax poetic for 2 minutes. Here we go. All right, not seeing too much here. So why is that? That could be having to do with our contrast, or it could be having to do with the telescope. But I think mostly it has to do with our contrast, because, oh, it's really, really tough, but you can see it's faint, right? Talk about low surface brightness. There's a galaxy. It's a spiral galaxy. Again, these stars are stars in our Milky Way galaxy that we're looking out through to see it. This is a spiral galaxy, and you could tell from this picture that spiral galaxies are flat, because this galaxy is seen almost directly, we call edge on. So we're looking at it right down the edge. If we could look at it from a different perspective, we'd see a big round thing, but we see it edge on. And what you can even tell from this picture, we should have gone 5 minutes, but we did 2 minutes, that this faintish stuff here, that's starlight, and there's this big dark thing running right down the middle. What's that, Maura?
That dark, yeah, that's dust in the galaxy that's basically blocking our view, obscuring light from stars that are in the background. You can see that in the Milky Way as well, since we're seeing it in a similar orientation.
Right. So people talk about the Milky Way. The Milky Way, of course, is a galaxy. We don't ever see the Milky Way quite like this or like Andromeda, because we live in it, right? So let's imagine living inside of it somewhere around here, and we look all around and we see along a line in the sky what's called the Milky Way. And that's because the Milky Way is flat. We live inside of it. So you look all around us and you see this line, and you can see dark things and bright things in there, and the dark things come from dust. Okay, we got any questions, Zach?
I have a few. I have one that just came in. So we here at NMSU also have the Apache Point Observatory. What do they observe? What type of stuff goes on at Apache Point?
Maura, why don't you take that question?
Well, there's a lot of stuff that goes on. I guess in terms of galaxy work, we're observing much more distant galaxies than these sometimes, or sometimes nearby galaxies like these, either with imaging or looking at their spectra, spreading the light out to see how much light there is at every wavelength. But we also do, there's people looking at exoplanets that are going in front of their stars, looking at the stars themselves, at how stars pulsate. There's a whole range of science that's done at Apache Point.
So actually, maybe that's a good segue into you talking a little bit about some stuff about galaxies and maybe highlighting a few things that are going on at NMSU. And you just tell
Yeah,
me
definitely.
move along here.
Mm-hmm. Yeah, so let me just get started. So I wanted to just give some highlights of some of the things that we know about galaxies and some of the questions that we're particularly interested in answering about galaxies, certainly here at in the department at NMSU. And so I wanted to start by just kind of pointing out that, this evening we've been, in a sense, exploring kind of our backyard. And when we were looking at the Andromeda galaxy, or maybe into the neighbor's yard when we were looking at NGC 891. But this picture here is just giving you kind of a graphical representation of where things are. So the Milky Way is down in the lower right, and then you have Andromeda up in the upper left. There's another large-ish galaxy, M33, that's sort of over in the same part of space. And this together, these three bigger galaxies and then a lot of smaller, what we call dwarf galaxies, are part of this, what we call the local group. It's our local neighborhood. Can you go to the next slide? Thanks, John. To start, I just wanted to point out that, so as we saw in the images tonight, you can see sort of the bright center of the galaxy where there are lots of stars, and a galaxy is a collection of stars and gas and dust and dark matter, as we were talking about. But when you're looking in the optical, it's really dominated by the light from many billions of stars. And on the right here, you see a much deeper image of the Andromeda galaxy than we were able to take tonight. To do this, to get this level of detail, you just need to stare for a very long time. It takes a lot of patience to be a galaxy observer. So this image on the right was taken by a telescope, not too much, pretty similar to the one that we used tonight, but I think it was a 90-hour, equivalent of 90 hours of exposure time to get all of this detail. So you have to be patient, and it helps also if you can go above the atmosphere. So the little part in the upper left there with that weird outline, that's the region that was actually observed with the Hubble Space Telescope. And you can see on the left image there, that's what it looks like, getting a much sharper view of the contents of the Andromeda galaxy, all the stars that you can see there, and then also you can see some of the wispy dark dust galaxy as well. And so just my sort of theme for tonight is that, from a human perspective, when we take a snapshot of a galaxy like we saw tonight, they look relatively static and unchanging, but actually there's a lot going on. And so one of the things that's going on is that all of the stars in the galaxy are going through a life cycle. Their stars are fusing heavier elements in the core of the star, and then those heavier elements end up enriching the next generations of stars. So one thing that people at NMSU, including John Holtzman and his group, are doing is using data from the Sloan Digital Sky Survey, which is a survey that's based up at Apache Point, to look at the chemical composition of stars in our own Milky Way. So individual stars in our own Milky Way, looking at their composition, their motions, to in a sense kind of get at an archaeological record of these past generations of stars in the galaxy. Another thing that's going on in a galaxy is not just, there's the evolution of past generations of stars, but also they're forming stars now. They're taking gas in the galaxy and turning it into stars. They're kind of star formation factories, if you want to think of it that way. And so in this image here, what you're seeing is a very deep image of this other galaxy that's in our backyard, the Triangulum galaxy, or M33. And in this image, John was mentioning using different filters to understand how much light there is in the blue or in the red, et cetera. And that's what's been done in this image. There were images taken in different filters and then spliced together to create this beautiful picture. So you can pick out the blue light of very young stars that are kind of tracing out the spiral pattern of this galaxy. You can see some of that sort of brownish stuff, that's dust obscuring light from the galaxy, kind of in the center. You can really see it pretty well. And then I wanted to highlight these sort of pinkish patches in this image. Those are regions where some stars have just turned on. when I say just, I'm saying in sort of in astrophysical timescale. So, you know, in the last 10 million years or so, which is a long time for a human, but it's kind of a blink of an eye in terms of astronomy. And so in these regions where you see this pinkish light, that's actually really massive, very hot stars that are causing their surroundings to glow. And so I've zoomed in on this one on the left side of the slide here. You can see, actually, if you look carefully, you can see the hot young blue stars in the center that are responsible for lighting up this whole region. That's one thing that galaxies are doing. And sort of along the same lines, all of these new stars that are forming in a galaxy, some of them live fast and die young in the sense that they go through their fuel really fast and then they explode in dramatic supernova explosions. And that, you know, all of the heavy elements that the star has made then gets blasted out into the surroundings and into the material of the galaxy. And when you have lots of stars forming in a galaxy and a number of them going off as supernovae, the combined effect creates sort of a bubble of pressurized material that blows stuff out of the galaxy. We actually call it a wind, a galaxy wind that drives material out of, you know, off of the disk of the galaxy. So this picture here is M82, sometimes called the cigar galaxy. It's another good one to look at. And you can see that they've, again, in this picture, used multiple filters to kind of pull out the different colors that tell us important information. And what you're seeing in the blue is sort of the disk of the galaxy seen edge on, kind of like the NGC 891 that we looked at, the last galaxy we looked at. But then the red is basically gas that's being blown out in a wind on either side, you know, off of the disk out of the galaxy. So this is another thing that galaxies are doing. And you can't see it in this picture, but should also be gas falling into galaxies, you know, fresh material coming into the galaxy that allows them to continue forming stars. All right, another thing that galaxies are up to, again, when you look at one of these snapshots, they look static, they look unchanging, but they're actually in motion in a lot of different ways. John talked about Vera Rubin's contributions, looking at how some galaxies are rotating. And she did that by measuring the speed that material is moving in different parts of a galaxy. So in this little graphic on the right, you can see, you know, on one side or where it says C, you can see the material is supposed to be going away from us. And that creates a shift actually in the color of the light that we see. It's called the Doppler shift. And so we see light being redder on one side and then correspondingly shifted to the blue on the other side. And by measuring how much of a shift there is, you get a measure for the speed. And that's how she did that measurement. So galaxies are rotating, some of them. Others are like M32 that we looked at that are more elliptical in shape. Their stars are moving, but not in the same sort of rotating all together in one direction. In that case, the stars are buzzing around, kind of in all which way, like bees buzzing around a hive. Galaxies are also, actually, just one more point about that last slide, just that galaxies are rotating or their stars are moving internally, but they're also, as John pointed out, moving towards each other because of gravity and then expanding with the universe as the universe is expanding sort of underneath them. All right, so as we saw tonight in the images, the galaxies are very bright in the center, and then they kind of, you know, get fainter as you go farther out. And then they can, you know, they fade away pretty quickly, and they may look somewhat like they're, you know, just floating out there alone in the blackness of space. Here's an image of Andromeda and the other galaxy in our local group, Triangulum, where you have a nice wide field of view, and you can actually see both of them in the same image, and no other galaxies in between. You see some stars; those are stars in the foreground from the Milky Way, but in this image, it's really just these two galaxies. So it kind of looks like that, but in reality, galaxies are very much not alone. So yeah, go back to this picture of the local group, where you can see, you know, Milky Way, Andromeda, Triangulum, M33, and then lots of little dwarf galaxies that are all orbiting around the bigger galaxies in our local neighborhood. And then if you zoom out even farther, what you see is lots of groupings and clusters and even superclusters of galaxies that are sort of extending in different directions away from the local group. The local group is, by the way, labeled in that blue. You can barely see it, that little blue label there in the center. So galaxies are very much not alone, and actually it's even more than that. If you were to look in any direction on the sky, you would see galaxies. And I wanted to just give a sort of a sense for this. If you were to think of the full moon, size of the full moon, how it looks to you on the sky, and think about a patch of sky about 1/10 the diameter of the moon. So something about the size of this little green, this little patch here. And if you were to look at that patch for a long time with the Hubble Space Telescope, this is what you would see, okay? So this is called the Hubble Ultra Deep Field. And it's a cumulative exposure time of something like 11 days, just staring at this one little patch of sky. And what you see in this image is just teeming with galaxies. If you look closely, you see different colors, different shapes. There's certainly different distances, galaxies at many different distances in this one little image, but pretty much everything in here is a galaxy. And this is just one patch of sky. So in any direction you look, you would expect to see the same basic picture. So there are galaxies everywhere. And if you were able to look even deeper, you would find that galaxies they're not just distributed sort of evenly all through space. They actually form a sort of web-like pattern. So the universe is actually kind of filled with wispy strands that are connecting each other. It's traced out in dark matter and gas and galaxies. We often refer to it as the cosmic web because it very much looks like sort of a web-like structure. And you can think of the galaxies as kind of being sprinkled along this cosmic web like dewdrops on a spider's web. So I put this little spider web image here because it's a fairly good analogy. There's lots of galaxies clustered together where the strands come together, and then there's very few galaxies in the gaps between those strands. And so here at NMSU, one of our very new faculty members who just joined us this year, Joe Burchett, is working on using interdisciplinary techniques to study and visualize how galaxies are distributed throughout the universe. And he's actually using another biological sort of analogy, the patterns in slime mold, to try and see how well that describes the patterns in this cosmic web. So some of the questions that I sort of want to leave you with that we're interested in understanding about galaxies has to do with how galaxies interact with their environment, this larger environment that I was just sort of describing. So for example, how does the environment affect the properties of galaxies, their colors, their shapes, the populations of stars that form inside of them, the amount of gas, all these sorts of things. How does the environment affect that? And how does the galaxy then affect its environment? For example, through the galaxy winds that I was mentioning earlier. Another question, back just one slide, John, if you could. Another question we're interested in is how much of the gas outside in this cosmic web is sort of pristine fuel that's going to be falling into a galaxy for the first time to fuel the formation of stars in the galaxy, and how much is enriched material that's sort of like exhaust that's been blown out of the galaxy. And then the last question might be, how does all of this cosmic gas out there, how is it changing over time as the universe is evolving? And so this picture that I'm showing on this slide is actually an actual picture. It's taken by the Subaru telescope, which is in Hawaii. It's one of the large telescopes that John mentioned at the beginning. And it's of a very distant patch on the universe. The blue light that you see there is actually light coming from hydrogen gas along these wispy strands. And the little white little white knots that you might be able to pick out, those are distant galaxies that are strung along those strands. All right. And so lastly, I just wanted to highlight some of the things that at NMSU we're working on in terms of answering some of these questions. So for example, in my group, we're using observations from large telescopes to study regions that are they're nebulae, basically very big glowing clouds of hydrogen gas in regions where groups of galaxies are forming. And so the image on the left here is one of these nebulae. It's about 300,000 light years across. It's a huge object, much bigger than an individual galaxy. And we're using data from the Very Large Telescope in Chile to map out how this gas is moving and where it's located relative to the galaxies in this region. The little black crosses you may be able to see, those are locations of galaxies. In the middle panel here, so this is work from Chris Churchill and his group, and they're using, one of the things they're doing is looking at the light from bright background sources, like a bright background quasar, and looking for signatures of gas clouds that lie in between us and that quasar. So the middle panel here is just showing some of their spectroscopic data where they've spread the light out to see how much light there is at every color. And then looking for signatures. And so the little colored bands you see in this figure are basically places where they have evidence for ionized carbon clouds that are along the path towards this bright background source. And then finally, Christian Finlater in the department and his group that are using simulations that they run on a supercomputer to try and predict what the composition and the distribution of gas should be like within this cosmic web. So on the right is you see some images for what they're predicting the oxygen distribution should look like at different times as the universe is evolving. And so by comparing their predictions of the real universe, their predictions to what we see in the real universe, they can test and hopefully improve our understanding of how and why the universe behaves as it does. So that's just a little taste of some of the things that we're thinking about galaxy-wise and also the larger cosmic landscape for galaxies.
All right, great. Thanks, Maura. So that brings us to 7:30, almost on the nose, our hour-and-a-half program. Hope everyone enjoyed a little mix up here about different stuff.